things, let's take a look at a purely pedagogical problem. For example, at this stage of the game, notice that I can't even talk meaningfully about what I mean by e to the z, nor by what I mean by sine z. I can not visualize z as an angle because it may be imaginary. I can't visualize it as a length in the traditional sense that we viewed functions from real variables into real variables. And the question that comes up is, how could I define e to the z and sine z? In fact, the cynic might say, why would you want to define e to the z and sine z? Now, one very cynical answer to the cynic would simply be that one of the most practical reasons for knowing how to define e to the z and sine z is that they will be on the quiz at the end of this particular block. But that's hardly a fair motivation. I will go into this in more detail later in the lecture. Let me simply point out that every time we have an analytic function, its real and imaginary parts define a conformal mapping. And consequently, every time we can meaningfully invent an analytic function, we have automatically invented a new conformal mapping. As I say, we'll go into that in more detail as we go along. But the question that now comes up is, how can I define e to the z? How can I define sine z, cosh z, all of these things? And one of the best ways of beginning is, again, to emphasize something that we said in one of our earlier lectures on complex numbers, that whatever definitions we invent, we want to make sure that the new definition does not contradict the old one. In other words, whatever definition I give of e to the z, I want to make sure that if z happens to be real, if I replace z by x, that e to the x has the same meaning whether I view x as a real number or whether I view it as a complex number. Now, one of the standard ways of doing something like this is the following. We, in part one of our course, had shown that the power series representation for e to the x was given by this infinite series, where this infinite series converged to e to the x for all real values of x. Now, what we can therefore say is, look at, if I just verbatim, every place I see an x, replace that by a z, and now make up the definition that e to the z will be summation n goes from 0 to infinity, z to the n over n factorial, then no matter what else happens, I'm sure that my definition of e to the z must agree with my definition of e to the x whenever z and x are equal. In other words, whenever z happens to denote a real number. Why is that the case? Because I got the new definition by lifting it from the old, just replacing the x by a z. The question that comes up, of course, is, what do you mean by this expression? What do you mean by a series when you're dealing with complex numbers? In particular, what it means is that given a sequence of complex numbers, I must define what I mean by a limit, and then go through this idea of defining a series to be a sequence of partial sums, and going through the same bit structurally that I went through in the real case. Now, let's do something that I think is very interesting over here. Let's just write down what the definition was for a limit of a sequence a sub n to equal L as n went to infinity. What was that definition in the real case? Limit, as n approaches infinity, a sub n equals L, means given any epsilon greater than 0, there exists a capital N, such that whenever little n exceeds capital N, the absolute value of a sub n minus L is less than epsilon. I hope this is very familiar to you. If not, feel free to review it. But here is the interesting point. No place in here do I mention that a sub n and L have to be real numbers. In other words, when I made up this definition, I assumed that they were, but notice that no place in here, in this definition, do I say that a sub n and L are real. In fact, where are the only places that I use realness? That since epsilon is real, I would like to believe that no matter what a sub n and L are, that the magnitude, the absolute value of a sub n minus L must be less than epsilon, means that the magnitude of a sub n minus L must be a real number, among other things, and in fact, preferably a positive real number. Notice that the magnitude of a complex number is still a non-negative real. Consequently, even if a sub n and L are complex, this definition still holds. And in fact,